Sure. Okay, well, welcome back, everyone. Thank you for coming to all 4 lectures. It's very nice of you. Today, I wanted to talk about something a little bit technical, and so I'm going to try to not give as many details as I could, which will, so I'm also doing a multimedia presentation. Okay. So this will be used very briefly. I just want to put some formulas up to refer to make it sort of clear what's going on. But what I wanted to do is, since the topic of my talks are quadratic forms and automorphic forms, I haven't said anything really automorphic yet. I've talked about the theta function, and so I wanted to sort of give just a taste, sort of a flavor of how one thinks about quadratic forms and their theta functions automorphically. Okay. And so for this, there's a language barrier, and I'm going to try to sort of ease us into it as much as we can, but not give too many of the technical details when I can avoid it. Okay? But if you have any questions, please feel free to ask. So in particular, I'll try to define what an automorphic form is, and use the idea of lifting automorphic forms from one group to another to produce the theta function that we all know and love. Okay? So that's sort of my goal for the talk today. And if you have any questions, again, please feel free to ask. Okay. Great. So the motivation was to try to understand the Siegel formula for local densities. But we want to understand it somehow in terms of representation theory. Okay. And so in an effort to do this, Weil introduced what is called the Weil representation now. Sometimes it's called the oscillator representation, to try to reinterpret Siegel's formula representation theoretically of representation theory. Okay. So the Weil representation, to construct it, would take a really long time. I certainly can't do it here. So what I'm going to do is I'm going to start with the Weil representation at some point just as a set of formulas that define a representation. You have to trust me that there really is one that exists and satisfies those things. And I'm going to try to use those formulas to just explicitly construct a theta function for you. Okay, so I just want you to see how the machine works. Okay. So in order to do this, it's important to understand things adelically. So this is sort of the big language barrier. So if people haven't seen adels before, basically what it tries to do is it takes something over the rational numbers, and it tries to be fair to it in terms of all of its completions. Okay? And so you can think about the rational numbers inside of the real numbers, or the 2-adic numbers, or the 3-adic numbers, or the 5-adic numbers, inside of all of them. And so basically what it is, it's going to be a product of all of these numbers together. But I don't want to take all the product of everything, because a rational number, it can't have denominators at every prime p. Okay? And so the idea is just that you can look at some sort of subset of this called the restricted direct product of all of these p-adic spaces and the real numbers, and that's sort of the right place that the rational numbers sit inside without too much extra space. Okay. So that's the idea. So what I'm going to do is define the adelization of an algebraic group, which I'm going to take to be either the group G is equal to SL2, or H, which is going to be the orthogonal group of some quadratic form Q, okay, or of some vector space. Okay. I'm going to define this to be just in the same way that you define the adels. I'm going to define the adelization of the group, so GA or HA, is defined to be this product over all places of the group over QV. But it's going to be restricted, and so this prime means that where all but finitely many components are in G of ZV. So that's what I'm going to mean by the adelization of an algebraic group. And so an element here, I'm going to note by G sub some boldface A for adels. And this you should think of as a tuple, an infinite tuple, g infinity or g minus 1, depending on how you feel about the real numbers, g2, g3, g5, and so on, one for every place. Okay? Oh. All right, the miracles of technology. Sorry, I must have hit something. Okay. Okay, that's good. Larger than life version of the Adele's. Okay, so if you weren't scared before, you should be really scared now. Okay, so the idea is that we can understand automorphic forms better adelically. Okay? And the reason is that we're being sort of more fair in the way that we think about them. We're not singling out the real numbers. We're thinking about them in all of these places at once. Okay, and so the reason this comes up in terms of theta functions is because you can talk about the adelic orthogonal group. So let me just fix some quadratic form. So some quadratic form. This is over the rational numbers. Okay, so or sometimes you write it as VQ, some quadratic space over the rational numbers. And I want to look at the orthogonal group of this form. Okay. So then there's the orthogonal group of Q. And the adelic orthogonal group, it acts on the vector space. Okay. So I want to sort of explain how this works. So this is, again, this is a product, right? This is the restricted direct product over all of the, be really careful here, OV of Q. Okay. It's a restricted product. And I claim that this acts on lattices in the vector space VQ. Okay. So I want to explain how this action works because it's really kind of cool. And this example hopefully will convince you that this is the right kind of way to understand a genus of quadratic forms. Okay. So let me start with a fact. And the fact is that if you have some lattice, L, which is contained in some vector space, V, it doesn't need to have a quadratic form on it, okay, then you can associate to L some collection of local lattices for all places V. So you can just look at the lattice inside of the vector space over Q2, Q3, the real numbers. It gives you some sort of lattice. Okay? But now I'm going to take the real numbers and forget about it. So I'm going to take V not equal to the real numbers, or not equal to infinity. Okay? So I'm going to just look at the local lattice at all of the primes. And so I claim that if you get a lattice and you sort of localize it at every prime, okay, so this is p-adic. Maybe I should call this P. Okay. That's better. Then this correspondence is bijective. Okay. And so if I start with a lattice and I localize it, determines, so then you can do this, and the collection of local lattices, L sub P, determine L uniquely. Okay. So what this means is that you can understand a lattice, okay, just by looking at it locally at all the prime places. Okay. And you can recover it, I mean, not as some abstract thing, it's something sitting explicitly inside of a vector space with a basis. You inherit the basis locally and then you lift. Okay. So if you believe this fact, then the orthogonal group, so then you can choose some lattice L sitting inside of the quadratic space. Okay. And you can act on this lattice by an adel. Okay. Act on L by the adelization of the orthogonal group locally everywhere. Let's say at all primes. So we start with the lattice L. So let's say I have an element of the orthogonal group. I'd like to understand how this acts. Let me call it H sub A. Okay, so this is going to be in the adelic orthogonal group. Okay. And I claim that this is going to act by taking a lattice to some other lattice L prime. Okay. So what do? You take L and you locally associate to it the set of all lattices over QP. It's localization. And then for each of these things, you can act by sending LP to HP of LP. And that's going to move your lattice around in your local vector space. And once you do that, then I have a collection of local lattices over here, and I claim that there's a unique lattice upstairs that realizes that. And so this gives you an action of the adelic orthogonal group on the lattice L. You might say, well, I'm not really being fair because I've singled out the prime places and not the Archimedean place. And that's true. I'm not being fair. Okay. So the Archimedean place acts trivially. Okay, so if you think about H infinity, this acts trivially on L. Okay. So that's the framework. So now we have an action of the orthogonal group on these lattices. Let's see what we can do with that. Okay, so I claim that we can use this idea to understand the genus of a quadratic form adelically as an intrinsic property of this group. Okay, so that's the idea. So to understand the genus of L adelically. So let me explain how that works. So you have, if you fix a lattice L, okay, inside of VQ, then I have a map from the adelic orthogonal group of Q. So this is going to take a lattice and locally move it around everywhere. Since it's an orthogonal transformation everywhere, it's going to be locally the same lattice. It's going to look locally the same. Okay? So I claim that this is going to take lattices. So this is going to take L to something in the genus of L. This is by taking L and sending it to, it's taking H, HA, and sending it to HA times L. This is going to vary over all lattices in the space which are locally equivalent to this one. Now, this action, it does a lot of things. There's a lot of information here that you can get rid of. So for instance, there are a lot of elements in the adelic orthogonal group that fix the lattice. And so you can mod out, this is really an action of this modulo K on this, where K is equal to the stabilizer. This is the adelic stabilizer of L. Okay. That means that at every local place, I'm stabilizing the local lattice. Okay. That's not going to change the lattice that I get over here, and so that this is an action, a well-defined action from this. And then I'd like to say when two things are equivalent in the genus, and they're equivalent if there's a global rational transformation that takes one to the other. This is the lattice interpretation of quadratic forms. So I can map this to the classes in the genus of L. And so if you'd like to see when two things are equivalent, then it means that they differ by some rational transformation. So this is now a way of realizing the classes in the genus of L. So, and that's kind of cool. So K here is some open, say some properties of it. This is an open compact subgroup of this orthogonal group, okay, containing the real place. Okay, so because the real place acts trivially, it's also contained in there. Okay. So what does this do, this construction? It lets you interpret the genus in terms of the orthogonal group. Okay. And it tells you that the size of the genus, the number of classes, is equal to the number of double cosets here. Okay. Now, admittedly, this looks a little more complicated than when I said the genus of the lattice, okay? But it has the advantage that it's sort of more canonical, and there's a group attached to it. Okay? So we can do something on that group, which we couldn't do before when we just had the genus. Okay, so that's the idea. And so now what we'd like to do is we'd like to use this to lift modular forms. Okay, so the idea is that we'd like to interpret the map which takes a quadratic form, or equivalently a lattice, and associates to it the theta series as a lifting of modular forms. Okay. In terms of lifting, so how does this interpretation that we have of the genus help us? Well, we're taking what we're doing, one way of thinking about it is this lattice defines a class in the genus. Okay? And so in terms of this picture over here, we should go back to this, the lattice is going to define a point in this set. And you can think about this set, I guess the picture, it's kind of a silly picture, but I'll draw it anyway. Okay. The picture is that there's a finite set of points here, and this is the genus of L. Okay, so there's L is here, maybe there's L prime, L double prime, L triple prime. These are all different points in the genus. And so I'd like to interpret something as coming from just one of these lattices. And so it's not completely unreasonable to define a lifting from a function on this orthogonal group, which just lives at that one lattice. Okay? So we do this by defining, I guess by noticing that functions on a group are sort of trivial modular forms. So a modular form is something that transforms in a certain way when you act on it. If it doesn't transform at all, then, well, it transforms in a nice way when you act on it by multiplying by 1. And so you can think about this is a modular form, just a function on this group, and then we'd like to take a function on this, just this coset, take a characteristic function of that coset and lift it. Okay. So I'm thinking about lifting. So here we define phi sub L to be equal to the characteristic function of the coset L, the class of L, in the genus. Okay. And so what we're thinking about in terms of the picture, this is the genus, is you have a function which is on L, takes the value 1, and all the other things, it takes the value 0. And that's a modular form for the orthogonal group. Okay? A silly modular form, a really silly modular form. But I'm trying to say it in a certain way. Yes, I'm trying to see this as a lifting. So then what you'd like to do is you'd like to somehow get from some function on the orthogonal group, so this is a modular function on the orthogonal group, I'd like to somehow put it over here. Now where is over there? Over there is a theta function, and the theta function is a modular form for SL2. Somehow I have to get to SL2 from the orthogonal group. Okay? And the way that you do that is that you try to find some really symmetric function, some kernel function that you can integrate against to move you from one group to the other. Okay? So then we'll try to lift phi L to a modular form on SL2 adelically, okay, by integrating against a nice kernel function. So that's the idea. So let me sort of write down what I mean by this. This is just the philosophy. Okay, so I want you to feel as though we're doing something that we're used to doing up here, but I'm going to do it in a slightly different context now with an orthogonal group sitting around in this picture. So how does this work? So explicitly, we'd like a kernel function which I'll call capital K of G and H, with a lot of symmetries. And when I say a lot of symmetries, I mean the symmetries that define a modular form on the orthogonal group and on the symplectic group, on an SL2, sorry. SL2 is a special case of the symplectic group, so sometimes I'll say that. Okay. So with a lot of symmetries, and then we can define the lifting. So theta L, I think it's called. The capital theta is the theta lift of this function. This is a function of the orthogonal group. So I'd like it to be a function on the symplectic group. This is on the orthogonal group, both Q. And we'll take G to be in SL2 to be the integral over this product. Let me say it differently. Let me just write it first, then I'll say it. The integral of this kernel function against this function phi L of H dH. So let me say where G and H live. So H is now in this orthogonal group, and everything's adelic. Okay. So the idea is that this function here has the symmetries of being a modular form on the orthogonal group, and this function has the symmetries of being a modular form in both groups. And so if I integrate the H part out, the orthogonal group part out, what's left will still have the symmetries of being an automorphic form on SL2. So that's the idea, is that the magic of what's happening here is in the kernel function. So if I could find a very symmetric kernel function, then I could do this, but how do we find that? Okay. So symmetries of this kernel function come from representation theory. Okay, so they come from representation theory. And in particular, they come from, we're going to make it with the Weil representation. So I'm just going to make a comment or two about how the Weil representation comes about, and then I'll try to define the kernel function and actually use it to do a lifting. Great. So the idea is that we can define the Weil representation, which I'll call W, as a representation from some giant symplectic group to some space of functions on the vector space of the quadratic form. Okay. So this is some big representation that someone makes somehow, okay, in some nice way. And inside of this, we have sitting both an orthogonal group and SL2. And so, so here are the variables. So I'll call, sometimes this is called H and G. So I'm using H to denote something in the orthogonal group and G in the SL2. And the idea is that this has enough symmetries that when I look at the restriction of the Weil representation to this, so this also gives me a Weil representation, then it has the symmetries of being a modular form with both the orthogonal group and the symplectic group. Okay. So just for your reference, if you restrict the Weil representation to this, these formulas here, these three formulas, define how it should act. Okay. So, okay, never used one of these before. Okay, great. So, so the Weil representation is it's a representation on SL2 across the orthogonal group. I'll tell you how it acts with the orthogonal group explicitly. It's very easy. Okay? And this is how it acts with SL2. Okay? So here, I guess a little bit complicated. So phi is a function on the vector space V. And the Weil representation is going to act by elements in SL2 on this function to give a new function on V. And so this is the formula for the new function in terms of the old function phi for every one of these elements. So there's just some formulas, right? There's nothing amazing here to see, except that I claim that this defines the Weil representation because SL2 is generated by diagonal elements, these upper triangular elements, and this one element, 0, minus 0, 1, minus 1, 0. So this defines a unique representation if it exists. And there are some cool features of it. One of them in particular is this feature number 3. So this is one particular element that we're talking about. This is the transformation that, if you think about it on the upper half plane, takes z to minus 1 over z. Okay? And that acts on functions by taking the Fourier transform. I didn't define it in this slide, but this phi hat is the Fourier transform. Okay? So the Fourier transform is sort of built into the Weyl representation, and that's a really useful thing, because when we were proving that a theta function was a modular form, we had to take a Fourier transform at some point. Okay. Okay. So let me define what this theta kernel is, and just make a comment about it. So the idea behind the theta kernel is just that you take your favorite function, and we're going to use the representation to average it in some nice way. Okay. Now, when you talk about the usual theta function, we always think about it on the standard lattice, on some x1 through xn, where your quadratic form lives. It's on some lattice. And so the idea here is that we average k of gh is defined to be a sum over a lattice of the Weyl representation acting on our favorite function, phi. And I'm going to sum it over all vectors v in some lattice, and the lattice is going to be the orthogonal group over the rational numbers cross SL2 over the rational numbers. So I don't really want to get into it too much. I just want to show you that this kernel function is defined as an average of a representation against some function. And I'm going to choose a particular function to do this lift. So I'm going to choose the function phi to be equal to, at the real place, e to the minus 2 pi times q of v. This is at the real place, times, so this is at infinity. And then the other places times the product of the characteristic functions of zp to the n. So what is this doing? This function is saying that it's supported on a standard lattice at every prime p. This is a lattice built into this function, and there's this decaying exponential that we have the usual Gaussian from the Fourier transform. Okay, so this should sort of look like I'm building a theta function in terms of pieces. I'm summing something over a lattice. The only thing that's a little bit strange here is the lattice that I'm looking at are the rational points, okay, not the integral points. But this is a lattice inside of the adelic orthogonal group cross SL2 at A. In the same way that the rational numbers sit really nicely inside of their adels, they sit discretely. Okay. So this is a lattice sum, but it's the adelic version. Okay. So this is a kernel function, and you can actually work out what this is in terms of h. The h action is really explicit. So if you just want to use those formulas to see how g acts, you can do that. So h acts just by multiplying v by h inverse. So this is the representation of that times h inverse v. Okay, and this again is the sum over the same v. So this is a very explicit way of writing down a kernel function, and the claim is that this has a lot of symmetries. So let me just see why this has a lot of symmetries. Invariant under the action. Oh, sorry, this doesn't make any sense. This should be in the vector space q to the n. Oh. Sorry. So what am I doing here? V lives in some vector space. It's the vector space of the quadratic form, and I have a lattice inside of that, and that's just the rational lattice q to the n inside of the adels at every place. Okay, so I'm sorry, that doesn't make any sense. This is a lattice in the adelization of V. Great. So the claim is that this, this kernel function is invariant under left multiplication by both the group SL2 of A and SL2 of Q and the orthogonal group of Q. So this is going to be symmetric with respect to both of these sort of lattices inside of the groups. And the reason that this is true, this one is easy. This is because here what we're doing is we have a lattice, q to the n, and we're summing over a lattice. And if h is in the rational orthogonal group, it's going to take that lattice to itself. Okay. So this is just from the definition, because when I do this to it, when I take an orthogonal transformation on a lattice on q to the n, it's again rational. So this one is harder, but it follows basically just by Poisson summation. So the reason that this is true is because basically you need to look at how each of these elements acts, and the important one is this element 3. Okay, so this element is going to act by the Fourier transform, but the function that I've written down here, phi, when you act on phi by the Fourier transform, at every place it's self-dual. It's equal to its own Fourier transform. And so this depends on phi, on our particular choice of phi. Okay, so we've done it in such a way that this has the symmetry. Okay, so I am rapidly running out of time, which is not so good. But the idea is that now we have this kernel function, okay, and we'd like to use this to lift our modular form. So let's see, what's the best way to say this quickly? So what I wanted to do is to say a little bit about what I mean by an adelic modular form on the SL2 side. I am not sure if I'll have time to say that. So let me just make some quick comments. Forms on SL2. So usually, if you have a modular form, you think of it as a function from the upper half plane to the complex numbers. Okay? And this is a function which is holomorphic in various symmetries, and f of az plus b over cz plus d is equal to, well, there's maybe some character, let me neglect that for right now, and just say it's something times cz plus d to the k times f of z. It has this transformation property. And what you can do is you can associate to this a modular form on the group SL2. And so this, let me just explain how to do that. The idea is that I have a map from SL2 of R to the upper half plane. And so you can sort of think of something on the upper half plane and pull it back to SL2 of R by composition. And this map, it takes AZ, A, B, C, D to its action on I, AI plus B over CI plus D. So you can really think of the upper half plane as sort of a flattened version of SL2 of R, and the kernel of this map is SO2 of R. So what you can do is if you have some modular form here, you can try to lift it to a modular form up here, something that transforms in a certain way. And the recipe, PIE, is that we can define the lifted automorphic form on GA essentially to be the function downstairs. So I act by the real component here, f of g infinity of I. And then I'm going to untwist it. So here, when I transform in a certain way by an element, I multiply by cz plus d to the k. And so I'm going to untwist it by multiplying by cz plus d to the minus k. Okay. And here, z is really the point in the upper half plane. And this c and d are really the things from just this one component of the adelic thing. So here this is G infinity, G2, and so on, and it's really just coming from this piece. So this function here has certain symmetries upstairs, and so I just want to make a comment about that. This F tilde of GA is left invariant by, so if I multiply on the left, then what's going to happen is if I multiply by some element of the rational group, by SL2Q, then it's going to sort of pass completely through this transformation. This is a general property of automorphy, is you'd like it to be left invariant under the rational group. Let me just make a comment about why this is true. I'm not really going to prove it, I don't have time to, but there are some standard references I can refer you to if you want. So the idea is just that if you act by some rational element, then here you're just really acting through the real part, and when you act through the real part, this transforms by a cz plus d to the k. I've untwisted it by cz plus d to the minus k, and so it should be invariant. In general, you can also do this if you have a character, and then you see a real part coming in, and then there's some part from some other primes that divide the level of the character, or the conductor. So it's important, so if you have characters, to think about things in terms of the rational group, although here you can get away with it just in terms of the real group. Okay, so that's what I mean by an adelic modular form. It's going to be some function on SL2 with certain symmetries, and the most important one, since I'm out of time, is just to mention that it's left invariant by this rational group. And why is this important? Because when we wrote down our kernel function here, k, was left invariant by the rational group of SL2. So it's reasonable that when I do this lifting, that what we get in the end is going to be automorphic on SL2. Okay. Okay. So let me just make some quick comments about how this computation goes. I was hoping to sort of show you a little bit about it, but I've got 10 minutes. 15. Okay, great. All right. So let me just talk about how this representation actually works now. So here's the representation. Down here is the kernel function. So I denoted this theta here by k. That's what I wrote down on the previous transparency. And it has this invariance property. The theta lift is what I take my original automorphic form and I integrate it against this kernel. So I just want to go through that integration now, and hopefully you'll see a theta function pop out. Okay. So the idea is now when we take a theta lift, we'll start with our characteristic function on the coset L and the orthogonal group. And I like to define the theta lift as this integral over the orthogonal group, the adelic orthogonal group modulo the rational orthogonal group against this kernel function. This is h, and here, k of gh, phi L of h dh. And all this is adelic. So I just want to work out what this is. So the first thing you can do is you can try to understand this integral. It happens in several parts. The first thing is you'd like to be able to understand the integral over this quotient. Now the integral over this quotient is something that we understand in terms of the genus. Okay? So in order to understand this in terms of the genus, we'll rewrite this using the genus. And the way you think of the genus is it's a bunch of double cosets when you fix some compact subgroup that stabilizes L. Okay. So let me just say where K is defined to be, again, the stabilizer, the adelic stabilizer of L. So I'm just going to rewrite that a little bit so you see how it works. So this OA is now OA. It's a union over classes in the genus, and the classes correspond to elements that you can move from one lattice to the other with. And so there's some I in some indexing set of OQ times alpha I times K. This is just a sum over classes in the genus of L by our previous comments. So I'm sort of interpreting the genus now here. So I'd like this to have something to do with the form. And so you can rewrite this orthogonal group here, this adelic thing, in terms of this sum of double cosets. Now there's no avoiding using double cosets when you do these kinds of computations. And so the idea here is not that I can somehow cover it up, but I want to sort of explain the main features as I go through it. So if you're uncomfortable with them, just notice that there's a genus here, and I'm using the genus somehow. Okay. So when you do this, you can so you have now a sum over double cosets indexed by this alpha sub I, and you can try to re-express your sum in terms of the dependence on each coset. Okay, so then let me just make a comment. Try to see how the integral depends on each coset, meaning, i.e., how it depends on each class in the genus of L. Okay. So I'm just going to put up the computation to show how this works. But basically, the idea is that this is going to break up in terms of a sum over classes in the genus, and each class is going to have some contribution depending on something to do with how this adelic thing breaks up. Okay. And it turns out that the contribution is the automorphism group. It's 1 over the automorphism group for each class. Okay. So maybe I'll just make a quick comment. So the point is that each class contributes 1 over the number of automorphisms of that class. Okay. So I'm going to go through a computation now to show you how that works, but this is the upshot. I'm sorry? L is definite. Yes, I'm always taking L to be definite here because I'm talking about theta series. Although one can do this construction completely in terms of indefinite things, but then the adelic picture that I drew is wrong on the orthogonal group, right? It's not a finite set. Okay. Okay, so let me just zoom in here. This is right from my notes, so if you want to take a look at the notes later, you're welcome to. Okay. Or not. So this is the unfolding of the double cosets. I'm just going to zoom in a little bit more. No, a little bit more. Just so you see it. Okay. So here we started with something, we unfolded it in terms of the genus, here. Okay. Then I moved the sum outside. And then what I did here is I tried to complete these cosets by multiplying an alpha I inverse on the other side. The significance of this is that I don't change the volume because I'm translating by an element of the group, and this is an invariant measure. But I do change the way that this looks. And now if you try to interpret what this thing is here, that thing is exactly the stabilizer of the lattice Li. Because alpha is the thing that moves you from L to Li. And so you can interpret that in terms of the stabilizer of that lattice, Li. And there's some alphas floating around in here. You've got to be a little bit careful. Okay. But then when you take the quotient with respect to that, so I use the isomorphism theorem for groups, you go from here to here, it lets you pull out this compact subgroup for Li in modulo this thing. Now this is compact, and that's rational. And so this is just the automorphisms of the lattice Li. And that's the idea. Okay, so by doing this double coset computation, you get a sum over classes in the genus weighted by 1 over the number of automorphisms. And this would look familiar. This is what happens in Ziegel's theorem. Right? We always see 1 over the number of automorphisms appearing, and this is why. Now, I chose my characteristic function in a certain way. I haven't done anything with it through this computation. Okay? And so at some point I have to use the fact this is the characteristic function of just one coset, and what that does is it kills all the other terms. Okay? So I don't want to explain too much as to how it does that, because it's a little computation. I can't even slide it up. But I can take this out and just take a sum over that one lattice. So it gives me 1 over the number of automorphisms of the integral over just one open compact subgroup over just the stabilizer of L of something. Now, for those of you who don't do many adelic computations, this is an amazing thing. This is great, because here, this group that we get, the integral over k, that's a product of groups. There's no quotients. There's something at 2, there's something at 3, there's something at 5, there's something at infinity, and you can do them all separately. So it's a product of local integrals, and this is where you see sort of a local product formula coming about, okay, whenever you do these kinds of things. Okay. So let me just write the upshot on my slightly bigger piece of paper. So we see that the theta lift of this characteristic function, phi L, on GA, is given by some integral just over k, 1 over the number of automorphisms, 1 over the number of automorphisms of L, times some integral over k of just this theta kernel. So this is H, is in this adelic compact group. So this is now a local thing, and you can try to evaluate what this is. Right, and so now I need to sort of look inside of the kernel to see what's going on. Right, so let me just do that, and then I'll be done. So I just want to finish this computation, and I'll be done with the lecture. So we know that the kernel is a sum over vectors in the rational space of something, right? Of this Weil representation acting on G, acting on this characteristic function, on this phi that we chose, H inverse V. Okay. Now, we chose our characteristic function phi so that it is a characteristic function of Zp to the n at all p-adic places. So I have a sum over rational points in a space, but if the rational point has a denominator, then it's going to be killed in the sum. So this really converts to a sum over vectors in our lattice L. There's some okay, that's fine, of this acting WG acting on phi, H inverse V. Okay. So now we have a sum over a lattice, and we feel like we're getting closer and closer to a theta function, right? I have a sum over a lattice, I have a decaying exponential in here, and so all that's left to do is to really see, well, how does this act on this? Okay. So at this point we can also replace this because we can also replace this by just the infinity component. I'll not explain that, but you can replace it by the infinity component, by the same idea, by just looking at how the transformations act. Okay. So this means that this theta lift, theta phi L, of G infinity, okay, it's equal to the sum of this Weil representation, WG infinity, the vectors in the lattice, acting on now just the infinite component, so it's 1 everywhere else. This is e to the minus 2 pi q of v. So this Weil representation is acting on this function. This is just phi at infinity. And at this point we get to use something we know about the Weil representation, which I put these formulas up, but we never use them. I get to use how it acts on these elements and on these elements. So rules 1 and 2. So what I'd like to do is I'd like to understand how this lives on the upper half plane. And I have a function here on a group which is real. This is something in SL2 of R. So I'd like to push it down to something on the upper half plane. And so you can see that if I take the element 1, x, 0, 1, so if I take g infinity to be equal to this times square root of y, 0, 0, 1 over square root of y. This maps to the point x plus iy, which is z in the upper half plane. Okay, so this is in SL2 of R, and this is in the upper half plane. And so if I want to understand what this looks like on the upper half plane, I can just evaluate it on these elements. So now we get to use these formulas. So what happens? So first I evaluate it on this element. And this element is going to act through this formula by multiplying by the determinant of the element, the determinant of A, to the n over 2, and putting an A inside of the function. So this is equal to the sum over the lattice of W1x01. And then there's this element, but this element acts by taking y to the n over 2 times e to the minus 2 pi q of square root of yv. That's one element done. Then you need to see how this element acts. And this element acts by multiplying the entire function by this e to the 2 pi ix q of v. Okay. So this is, again, a sum of e to the, get it right? E to the 2 pi ix q of v. So I have this y to the n over 2. And I get e to the minus 2 pi q of square root of yv, but this is quadratic, so I can put a y outside, q of v. And this is sum over v in L. Now we're essentially done, because if you just rewrite this and see what it looks like, this looks like y to the n over 2 times the sum over vectors in our lattice, and this is e to the 2 pi ix q of v. This is e to the minus 2 pi y, but minus is I times I. So I can rewrite this as the sum over the lattice of e to the 2 pi I z times q of v. And this is essentially the same as the sum. So if you collect all the values collect these terms by their values, this is the sum over m greater than or equal to 0 of r sub q of m q to the m. And so that's the point, is that we have some explicit, concrete way of writing down the theta function, not just as some counting, but in terms of a lifting from orthogonal groups to symplectic groups. Okay? So, thank you.